The current panel that's coming up now is going to talk to us about the role of protected microgrids for community protection. It's a very distinguished panel. Leading that is the Honorable R. James Woolsey, who you know best probably as former CIA director, who is currently chairman of the Foundation for Defense of Democracies and a venture partner with Lux Capital. One of our panelists is late, I believe, still, or having trouble getting here. We do have Mr. David Geary from DC Fusion, Mr. Terry Hill from the Passive House Institute and Community Microgrids. So without any further delay, and we've got Chuck.
I'm just here as a foil if something is needed at the last minute, because I know we have to end this one on time. We're a little bit early because there's an unexpected requirement for
I got it.
Our guest to be on a television program. So.
Yeah, that's, we don't want it, so let's not get in the way. Go ahead, folks.
Pardon me? If you can. Yes, please. That'd be great.
Thank you. Well, thanks, Chuck, and I'm honored at the opportunity to talk to a very knowledgeable and distinguished group such as this. I want to start with a difference, a distinction that one of my colleagues at Stanford, when I was teaching out there a few years ago, came up with. She said we have to pay attention to the fact that we're dealing with both malignant and malevolent problems when we are dealing with EMP and the grid. And the solution is not always the same, although sometimes it can overlap. And sometimes instrumentality is the same. For example, smallpox is a malignant problem, but it's been used aggressively by giving Indian tribes blankets with smallpox in them in the early days of the Western civilization in North America. One can have the same instrumentality be used malevolently, but occur naturally and be malignant in at least a general sense, not precisely in the same way germs are malignant. Well, I think that or rather cancer is. I think the thing that is of substantial importance is that it is not going to be enough to fix the grid. I'm delighted to see the world stirring on this issue that several of us have been working on now for several years, and to see attention to resilience for the grid, to seeing some bestirring of activity on behalf of state legislatures and the like. And let's face it, there are a number of people who are willing, indeed eager, to work on malignant problems, but they just as soon not talk about the malevolent ones. Either because they don't want to have to go to the Defense Department for funding, or because of some other bureaucratic or political reason. There are just a number of people in government and otherwise who really don't want to talk or think about something like a nuclear detonation in low Earth orbit that would, with both long and short wavelength EMP, take out not only the grid, but also your individual devices. And we have to pay attention to that, and we have to find a way to deal with both malignant and malevolent problems. Hopefully, one can come up with solutions that overlap. What is the nature of the problems? Well, first of all, let's look at malevolence. This group is probably familiar largely with the events in Metcalf, Colorado, now nearly 3 years ago, in which a small group of highly disciplined young men with AK-47s, having trained exactly how to cut and take out the emergency alerts, carrying the right kind of tools to lift very heavy manhole covers amongst a group of transformers, systematically stood and took out with rifle fire a large number of the transformers that would have that supply and deal with Silicon Valley. virtually everyone connected with looking into that, except for the woman who was a local sheriff, wanted to call it hooliganism, which is a way of avoiding saying terrorism, sort of like saying workplace violence for something that looks an awful lot like terrorism. But those sorts of euphemisms don't let me have to think about an intentional group planning to take out large numbers of transformers with rifle fire. I don't want to think about that. I'd rather think about space weather. We got to deal with space weather. It's a very serious matter, and it could take out a huge amount of our electric grid. But it's not the only problem. And so not only for rifle fire, so-called kinetic threats, but also for radiation weapons, driving around Wall Street in a panel truck with the right kind of radiation generating equipment in the panel truck could do huge degrees of disaster to our financial system. And of course, most devastatingly of all, a nuclear detonation in low Earth orbit, and by low Earth I mean everything from 20 up to several hundred miles, and having that detonation be able to generate through the gamma rays both the long wavelength and the short wavelength EMP is a realistic possibility. We know that the North Koreans, in launching their, I think, 3 satellites and having tested 3 or 4 nuclear weapons, have taken steps to do it in such a way as to make sure when they are launching to the south to avoid having something come up over the United States from the north where all our sensors and radars are. You launch to the south in what the Russians called a fractional orbital bombardment system, and the satellite containing the nuclear weapon comes up from the southern trajectory, so you don't know that it's coming. The first thing you may know is that the lights go out, and you may not know whether it is space weather or whether it is a action by the North Koreans launching a fractional orbital bombardment system. As a result of the different ways in which we have to envision and deal with malevolent problems as well as malignant ones, we need to deal with this, I think, doubly. Yes, we have to take steps to build resilience into the grid. We're going to need the grid for a very long time, even if we have other emphasis. But there is, I think, also a real need, a major need to let Edison have a second crack at his war with Tesla, and to make it possible for direct current, distributed generation, without inverters, all of that, relatively simple, roof of your house, roof of the school, good storage, which requires, I know, some further development, but being able to have a simple system like that be resilient against electromagnetic pulse, both the chips and any interconnections, can make it possible in the event of space weather of some terrible sort or any other way of taking out electricity, can make it possible to defend against that. And I would say that steps to have moved toward even a partial independence and resilience by distributed generation, direct current, solar probably, although probably not exclusively, is a sort of thing that encouraging it would be good. whether it's through tax system, whether it's through pressing utilities to be more tolerant of microgrids than most of them are, whatever steps are necessary for us to be able to have at least the basics if something happens to the grid is essential and could be the difference between maintaining our civilization and not being able to maintain it. If the grid goes and we're not doing anything else, then the key one of the 18 critical infrastructures in the country is down, and the other 17, food, water, transportation, finance, all depend on the 18th, electricity. So if the grid goes, you are not back in the 1980s pre-web. You are back in the 1880s pre-grid, and very few of us have enough plow horses and seeds to live a 19th century existence successfully. Is it unpleasant to have to think about that? Yes. Do we feel sorry for you if you have to think about it? No. Think about it. Help us all figure out how distributed generation, with simplicity as its principal criterion and resilience, can help farmers, businesses, schools, homes, individual buildings with, let's say, solar on the roof and batteries in the basement, take steps to get by, even if it's not perfect, even if it's not everything the utility would supply to you on a good day. Even then, to be able to get by is the difference between the civilization being destroyed and it's not being destroyed. And we need to keep that set of values and that set of issues in mind as we look at some of the possibilities and how one can take useful steps in moving toward a world in which Edison and his direct current get a second chance. Thank you.
David Geary, would you like to tell us a little bit more about direct current microgrids?
What a great lead-in. Thank you. I was asked to actually provide an industry update on DC power and microgrids. And a lot of things, I don't know if everybody has heard about some of the activity, but you know, DC power is sort of regenerating in history. The war of the currents is, to some extent, is reoccurring, but in a different way this time, because we know that the grid's going to be there. And we know that there's new technologies that exist today that didn't exist back then. Today we have power electronics, and that's the difference between today and yesterday. That's the difference why we have AC power for the most part around the world. But now power electronics is offering some great opportunities to take advantage of a lot of the things that are happening around us and a lot of developments that are occurring as we speak. A great history book on how we got to where we are today, some current event ideas and things that are happening around the world that sort of emphasize a lot of the things that Jim just mentioned. This is Intel. Intel is very interested in the whole DC power concept. They see the next generation of what was the internet in prior years now becoming the internet, the energy net. Their focus, obviously, is that they see a great opportunity of a lot of things being connected to the internet of things, and all those things require chips. They also are looking at the other aspect of this, which is the fact that there's still, it's hard to believe, 1.5 billion people without power in the world. So they're looking at this as an enabling technology to actually help develop some of those undeveloped parts of the world as we speak. So where we actually all this started was actually in the data center. The data center, as you probably have heard, and all the things that are happening with the internet, in a few years, back I think they're projecting 2020, will be consuming as much power as the third largest country in the world, going over Japan and Russia and behind U.S. and China. The data center industry is exploding as we speak. And the base load in a data center is DC. It's a computer. The first thing that the computer does is take the AC power that is given, converts it to DC. So this is where the whole idea started, because the Intels, the Googles, the Apples, all of whom we've met with over these years, have said, what's a better way of doing things? So they've come up with the idea of going to a DC power infrastructure. 380 volts is becoming a worldwide standard of DC power because it's sort of a sweet spot and a lot of other things happening around the world with alternative energy and many other things. The IT manufacturers, IBM, Lenovo, are all coming on board and developing products and actually writing white papers that espouse the benefits of DC power. The history actually started about early 2000. 2004 was when I did my first demonstration project out at Sun Microsystem. In the middle is sort of the U.S. Time frame. And you can see that the world has sort of followed pace with that to where we are today. And at this point in time, we're seeing deployments around the world start to increase over time. I have to almost update the slide on a weekly basis these days. The problem, though, right now is that China and Japan have accepted this whole concept and are moving forward quite rapidly with it. The United States still has a lot of the things I think we've talked about here today as sort of roadblocks of allowing us to move at a faster pace along with them. Worldwide standards are in process and being written. Some are already existing and are edited, some are new, but the standards around the world are being developed for this. This is actually a white paper we just finished with the Society of Cable and Telecommunications Engineers. This is the cable industry. One thing that the cable industry really took notice of was Hurricane Sandy and all the things that happened to their infrastructure. They don't want to see that happen again and are looking for ways of implementing DC microgrids and other things that allow them to go island mode and survive some of these situations. So there's actually some white papers that have been written comparing AC to DC. So all these things are in process on the data center side to show what the business case is. It has to be a business case to show why we would convert from an AC infrastructure to a DC infrastructure, and these are some of the reasons why. More efficiency is how this all started, but then the AC world started to become very efficient as well. But there's a lot of other benefits that we'll see as we go through some of these other slides. It has to be a true business case. It's got to be safe. It's got to be reliable, it's got to be flexible, and it has to be efficient. There has to be a business case to make this change. So again, this is started in the data center. These are some few pictures of what a DC data center looks like, some drawings and proof of concepts and comparisons. So again, it started in the data center. From the data center, groups like the Emerge Alliance, which is an industry group that was developed to help promote the idea of DC power, started to get members, and you can see many of the companies that are now part of the Emerge Alliance that want to take this idea outside the data center and now are implementing this idea in office buildings with some of the benefits that occur when you go to DC and office buildings, as well as in microgrids and so forth. And there's been a few projects around the country that are showing this and are in process as we speak. So the whole idea is to try to go to a zero net energy building type of concept. And some of the things that, again, DC power offers is that there's always going to be AC sources and DC sources. There's going to be AC loads and DC loads. In fact, one recent report I saw is that probably over 80% of the loads that we have today are basically inherently DC. We still have a few incandescent light bulbs around, but all the fluorescent lighting, the LED lighting, projectors, and even the appliances in your home are being developed to operate on a DC power infrastructure. So a lot of benefits. The only thing we would need to do is feed a DC collector bus matching voltages and bring sources together to feed loads. With that, the integration of alternative energy sources, PV, energy storage, all sort of inherently DC power systems. So we're starting to see some of these projects being implemented as we speak. This is actually a data center in Ashburn, Virginia, that's testing out this whole concept of doing an integrated DC microgrid within a data center environment. We're looking at different ways of doing DC grids. Again, the DC grid is a much simpler concept than trying to put together alternating energy or alternating voltage sources when you have to synchronize and worry about phase shifting and so forth. We're seeing a lot of industry, cross-industry collaboration. We've got the alternative energy industry, a lot of DC sources. We have the electric vehicle market that's inherently about a 400-volt DC system that can plug right into a DC microgrid. You have the Department of Defense. The next generation ship that was just launched is all DC power. Again, there's benefits to that topology. In fact, the electric ship program has been going on probably for over 10 years before this launch, and they've gone through a lot of the research that's already have to take place to basically integrate a DC microgrid at a megawatts level size. DoD, obviously, they're interested in microgrids. They don't like delivering fuel to the front line. So anything they can do to come up with ideas and configurations that allow them to go to an off-grid islanding type of mode for DC microgrids is something that they're very interested in or are looking at, and all the benefits that come with that. We at DC Fusion basically started up this past year just to try and bring industry together, because as you would expect, there's a lot of new companies, small companies out there developing products and systems for this whole topology. They're small companies, but they're doing real projects. Pica Energy out of Maine actually does DC microgrids for high-end homes. Again, a place where the first proof of concepts are basically done because you have people interested in taking care of themselves and have the means to do that and want to make a difference in the world. So they're doing residence, but they're starting to scale up to commercial. You have some Canadian companies also doing their version of a DC microgrid, and all these different other folks that are playing in this arena. Not to mention Tesla and the Powerwall. If you haven't seen the announcement that Solar City is now offering microgrid as a service. The whole idea with that is taking the Powerwall from Tesla, integrating that into a DC microgrid on the meter, or on the load side of the meter. So the other things that sort of has happened with this journey is again looking at the benefits of DC power. There's energy savings, there's cost savings, and different universities and folks around the world. This is my friend Dr. Raj from Clemson, showing and trying to show the world again that there's over 1.5 billion people without access to electricity as we speak. This is enabling opportunity to change that, as well as all the other things happening, and he sees PV generated DC as an enabling technology to help get there. So we're starting to see this happen. This is a third world countries that don't have electricity as we speak, but they're implementing this idea and making things work. If we can see folks like this do this and develop and take advantage of what could be done in a very simple, very cost-effective way, there's got to be lessons that we can learn from them and to look at how we can maybe take care of some of these high-impact threats that we have to deal with. So we're looking at going from little village and hut ideas to neighborhoods, all integrating DC power. We're seeing some designs hitting the drawing board for sustainable communities, where you can basically have maybe a grid interface at the beginning of a neighborhood, but the whole neighborhood becomes self-sustaining because we're sharing alternative energy resources on a DC microgrid. So all these ideas are starting to percolate. We had our first conference, IEEE conference in June in Atlanta, on DC microgrids. We had folks from all over the world coming to give their presentations on what they're doing. Again, quite a bit of activity around the world. We'd like to see more of this happen in the United States. So again, some of the benefits of DC are the reliability. Less components equals higher reliability, and there's been studies that have proven that. Oops. Also, our friends in Japan, one of the reasons why they were big DC proponents and DC microgrid is that they were doing their own version of DC microgrid research back when the tidal wave hit. And the only things that really stayed up and running and were recoverable were the DC microgrids that they were in process of testing, and they've made a full-fledged investment in developing a more DC microgrid infrastructure. The other thing we're doing is now working with some software companies. As an engineer, I'd love to be able to design something, but also like to model it before somebody builds it and prove that it works. So we're starting to see those tools hit the market as well. Power Analytics that has software that allows you to model, analyze, optimize, build, monitor, control, and then transact. We're seeing the infrastructure and software being developed to allow us to build these systems, study these systems, model these systems on paper and in the computer Then we can turn those systems into the monitoring and control system. We then can start gathering real-time data. We can then start optimizing. We can then start doing simulations. We can start looking at, okay, what does an EMP event look like on this system that I just modeled in the software that basically is the utility system for this area of the country. And if you can model that on the computer, and then as things happen and more testing and data gathering is done, the model becomes that much more valuable and the data becomes that much more reliable. So we're seeing these things hit the market where you can model the system, you can turn it into your control system, and it becomes your real-time data monitoring, control, real-time arc flash, other things that you can do now with the tools that we have available. And this can happen with both AC and DC, integrated, separate, islanding, all the different modes of operation now are available because they can turn this control system into a microgrid power management system as well. So again, it seems like the perfect storm from my perspective. I'm an engineer, so instead of drawing single lines electrically on the drawing board like I've grown up doing, this to me is sort of like being in a candy shop, allowing me to build it in software, model it, play with different scenarios. And where this all is going is the energy net. As time goes on and these microgrids develop, they're going to be integrated with the real grid. There's going to be the internet of power out there, and everything that we're going to do, we do in the internet right now today, we will have the power apps to add to that as we develop the energy net. So, that's it.
Now, Terry Hill, if you could take, I think you have a couple of slides too, Terry. Is that the case?
Yeah.
And you could maybe mention what you're doing with, how would you best describe it for us that would differentiate it from what he just did? Because you have a very interesting approach to things that are being done in the residential area.
Thanks, Chuck. I'm Terry Hill. I'm on the board of directors of the Passive House Institute. And I came here in 2013 to my first one of these. And when I listened to the presentations, it became immediately apparent to me that what I was promoting, the idea of energy efficient buildings, was a core requirement to fit into all this. So I've been following Chuck around ever since. So last year, Virginia had to revamp its energy plan. So they had a listening session around the state. One of them I went to, and I had to have a context of what I wanted to say, so I suggested that we have a resilient reach building code. Now, stretch codes have been, Massachusetts has one actually, where the state offers individual cities and towns an opportunity to reach beyond the existing building code, and there's some sort of benefits for that. So that's the context that I went through this. A stretch code, you can all read it, I don't have to read it, a little bit stronger than the existing code. I threw the word resilience in. What's happening here? I'm going. There we go. Okay. So I threw this into the 3-minute presentation because 70% of the grid, the energy in the grid, is basically wasted, and we're paying for it. Nobody really talks about that. They talk about 10%, 15% maybe. But according to David and our friends Raj down there in Clemson, he maintains it's 70%. And I saw him argue that with a large, very important man from Duke Energy. So I'm using 70%. So resilience. I had to throw that in for the people on the Virginia Energy Commission. I like the idea. It goes beyond just what a passive house is. It's sort of, I'd like to see the Passive House Institute expand its idea of what it's promoting into resilience. When after Sandy happened, I'd never really been in a real bad weather event before, so after I drove up to that, and I'd just driven out to Oklahoma and looked at the results of the tornadoes, all of the idea of how do we increase the passive house building code to encompass all these things and make them better. And resilience is the direction I'd like to see it go. Now, the insurance industry come up a couple of times here. They're already sick and tired of paying out too much money, so they have their own building code now. And the Department of Homeland Security, I think, is picking up on that, and I think they're calling it Fortified Star. So, and DOE is also referencing this in its presentations. They're looking at, wind events, earthquakes, etc. And this fortified section, their initial effort is to at least build a code, but if you really want to do a good job, go to the fortified standard. Now, in a resilient building, you also want it to be, functioning, and you want to have good indoor air quality. And the reason I stuck this in here is because passive house is the only standard that requires an energy recovery ventilator in it, which gives 24/7 fresh air. So this is a passive house, or a depiction of it. Have you got that? Right there. Okay. 6-sided insulation. This red line here represents a part of the wall you designate as a air barrier. You don't want any air moving through the walls. Triple pane windows, and therefore you've got a very tight envelope, so you've got to take care of the indoor air. And this section over here is the energy recovery ventilator. So in they want 93% efficiency in these things. So you're losing very little of the energy that you've used to condition the air, and you've got the result is you've got a very high quality indoor air after it's all done. Now, this is a new home, or a depiction of a new home, but there's 78 million homes in this country that are existing, right? So, before I get to that, where does the passive house fit? This is DOE, May 2015. There's the little depiction that DOE's put out. Where does passive house standard fit relative to the other building standards? There's the current standard, or maybe it's got to 2012 now. Energy Star, and then there's DOE's Zero Energy House and Passive House as far as the energy savings position is right at the top. There's an existing house in California, retrofitted house. They're the results. Now, when you build a retrofit to this standard, you're going to save 80% or up to 90% of energy for heating and cooling. And this can be retrofitted, so you've dramatically reduced the load in the house. What are you left with? The plug loads, lighting, appliances, etc. David's already told you the impact that direct current can have on that. So another 30% savings from the plug loads if you had direct current inside the envelope. The PV on the roof produces direct current. The batteries use direct current. So a homogeneous environment with direct current inside there has dramatically reduced the load on the grid for that particular house. Now, if you expanded that to a city block and tied it all together with a direct current microgrid, now you're getting the sense of, an islandable microgrid with a dramatically reduced load is beginning to shift the nature of the grid. And if we could, scale it up, it changes the nature of things, at least from my point of view. Other people may not think that, but the possibilities. There are the plug loads. There's a little depiction of the house. The same picture that you got, Dave. Now, the interesting to me is inverters. in a little microgrid, you only need one point of contact with the big grid. The other houses wouldn't have to have an inverter. And right now, if you're connected to the grid with PV, if the grid goes down, you're down. Except there may be some changes in the later inverters that allow that to island. What else? There's another depiction of that. Wide direct current, we've already gone that. Resiliency, customer engagement, Internet of Things. You know, who knows what's going to come out when Apple releases its HomeKit on this thing. And of course I found out that in the last 2 days that these are sort of not affected by EMP and solar flares. So I never knew that. It's pretty interesting. But the final thing I want to mention is DOE's been working on this for years. It's, I don't know if anybody's come across transactive energy, but it's their effort to model and control distributed generation and to create a retail market for electricity. And they've only in the last 6 months begun to speak about this in the open. But here's something that we haven't seen too much about. The privacy, you know, right now the utility can tell when you switch the light on in your bathroom if they want to. And they can do it from the pole outside. And they really don't need smart meters from what I can understand. They can do it all with solid state transformers that are sitting on the pole. They can give you direct current out of that side or alternating current out of that side, doesn't matter. But with a microgrid, you can aggregate and you can hide behind the point of contact. And privacy is an issue that's really not being spoken about much. So with that, thank you very much.
Thank you. Since Ambassador Woolsey has to leave for an engagement that is a little bit unexpected, and then Dr. Baker is going to comment on his perspective on all of this. And I wanted to mention that so Dr. Baker doesn't think Ambassador Woolsey doesn't like him or something. But would you like to have a closing word before you go as you walk off? From goodbye.
This is all very interesting and important. I'm learning a lot, and I appreciate being invited.
Thank you very much.
Thank you.
Dr. Baker, you
Yes.
probably have lots of interesting
Well,
thoughts.
I'll keep my
your mind's going.
I'll keep my
100 miles an
comments very brief. I was originally supposed to be on the next panel, but this morning Chuck asked if I could. He thought this panel might be a little sparse. Asked if I could help with this panel, so I'll make my remarks here. My main observations are just some thoughts on making the smart grids. They offer an awful lot of promise, but we need to be thinking about their ability to resist EMP and GMD effects. And we're just at the ground floor. I mean, for instance, the IEEE, they just had their first international conference on this technology this year. So we're in a position where now if we act fast, we can design in the protection for EMP and GMD into the systems from the get-go. And the DoD experience is if you design in the protection, you'll save a factor of 10. Right? If you retrofit the systems, once they're deployed, once they're out, you have them out in the field, it's going to cost you 10 times as much to protect them. So that's one important point. These systems do offer a tremendous amount of promise. Especially, I'm very just fascinated by the data center applications because most of data center equipment rides on DC. You walk into a data center, and I've been in some very large ones that have acres of racks and use megawatts of energy. The equipment in those racks is DC powered and rides on DC, so that's an application that is really good. The other thought that occurs to me, my daughter went to St. Olaf College in Northfield, Minnesota, and that campus is powered by wind. They have wind generators. Of course, with their setup, the wind doesn't always blow, so they have to be able to and they're selling power back to the grid, so they're connected into the grid as well. So they have to be synchronized, the wind with the 60 cycle on the, and so ideally, if you can run your microgrid standalone, that's the best from an EMP and GMD standpoint. The minute you connect to the grid, all bets are off, and the inverters and the electronic synchronization that are required, those would need to be protected. You also have battery charge monitors and controls that need to be protected. The auto transfer switch, you want to be able to, if there is any kind of major transient on the grid, you want to be able to automatically disconnect from the grid to protect the microgrid. And so you need to design in protected auto transfer switches to enable the necessary protection and also load balancing. Of course, as the wind turbine or the sun goes behind the clouds, you need to be able to balance the load, bring it between the grid, your storage devices, and the renewable energy source. And of course, the photovoltaic cells themselves will need to be, since they're PN junctions, they're solid state devices need to be protected. So I think there's just a lot of possibilities here. If these things are designed correctly, you can make these systems from an EMP and GMD standpoint as hard as a rock. One other point that I should make, and just as I close here, one of the good things about transformers, when you have a system sitting behind a transformer, the transformers block DC. They block quasi-DC. They will block the GMD and the E3. And that's one of the great things about when I go out and look at big data centers, the presence of that transformer it really helps. If you have we need to be careful when we go to microgrids that have long conductors when they get to be out, if there are situations where you have DC conductors that are kilometers in length, the GMD quasi-DC currents induced by the sun, the solar effect, will be much larger, and that needs to be factored into the design. That's all I have. Yeah.
Thank you. Is there one question or two? If there is, you'd have to go to the microphone. I see Congressman Bartlett coming to the microphone.
Thank you very much for your presentations. I've been using solar systems for about 30 years now. And I use almost all of the power, almost all of the energy is DC energy. I had to go to China to get 24-volt LED bulbs. They would sell them to me in any wavelength I wanted, dimmable bulbs. We don't manufacture them yet in our country. Candelabra-based, standard-based bulbs. I use the energy as DC energy for one simple reason. I have inverters, of course, where I need to have AC power. But they're big, complex, computer-filled devices that are sure as heck going to fail in an EMP or a solar storm. And I would like to be comfortable after they've failed. My first array was put on a property on 153 acres. And I put them on the roof. Of course, that's where you put solar panels, is on the roof. And shortly after they were installed, I noticed that 1/8 of my solar panels weren't producing any energy. It was obviously something open up there. But because I could make do with 7/8 of the energy, and because it was really difficult to get up on the roof, I never did fix them. And then it occurred to me that the sun is 93 million miles away. And I'm not materially closer to the sun on the roof than I am on the ground. So I took them off the roof and I put them on the ground. So now I can more easily control, fix my solar panels and my roof with them on the ground. I don't see any reason for putting solar panels on a roof. The only reason for putting them on a roof is you don't have anywhere else to put them. And I noticed that even when they're showing them on a pedestal, they show that pedestal way in the heck up in the air. The sun is 93 million miles away. You ain't getting meaningfully closer to it up there. Thanks.
Any comments? Since the panelists may have a question of each other. We've got 30 seconds.
I have a question.
Yes.
Okay.
What about these advances that the White House is putting so much money into ultra-wideband semiconductors? That intrigues me. And how will they be hardened in the development process, as you mentioned? How can we foster that?
Well, you can actually build protection into the chips themselves, and that's being done by the semiconductor industry. And it turns out that the discharge, when you walk across the room and touch your radiator, you get a spark. That spark has current amplitude and pulse characteristics very similar to what you would get from an EMP. And so that kind of protection is built into many of the semiconductor chips, but you can do the same with the ultra-wideband electronics as well.
Yeah, that's a very good comment. One thing I wanted to mention is that on all these early proof of concepts for doing DC power, we're sort of being forced to make it look a lot like AC power because that's what people are used to using, and they're used to using circuit breakers and running things and installing things and panel boards and so on and so forth. One of the things, or many of the things that are going to come out in favor of, I think, DC are the advances and the advantages that DC does provide, and there's things that haven't even been invented yet, but things are starting to be invented. Solid-state circuit breakers will replace typical rocker switch circuit breakers in the future. They'll be much faster. They'll have things built into them, safety-wise and so forth. Safety and grounding, a whole new issue that different options in DC power are offering. There's another company that just announced a new product called Volt Server, if you ever want to Google Volt Server. But it's basically taking the communications concept of doing packetized internet communications and turning it into power. You got a power signature now that goes out to every load. If something happens to that signature along the way, it knows exactly within microseconds that something's happened, and they're developing protection schemes with that. So a lot of these different other technologies and other enabling advantages of DC power, quite frankly, coupled with some of the things that we're looking at for EMP protection and other things, if we bring the group together to look at these things specifically, I think there's quite a bit of opportunity there that could be very exciting.
So this goes back and speaks to the value of all of us, for example, in the technology, and to come with our technology societies, all the IEEE organizations and COSI, and look at this from the big picture perspective. How do we keep everything viable by being more resilient in the first place, and create a culture from the inventor down to the people who deploy and consume that think of this, and the whole distributed side of things, which basically says, I'm not a helpless victim anymore. I can be more resilient myself and with my friends in my local community, and not only take responsibility for it, but enjoy the comfort of being able to do something for myself and my neighbors. And thank you very much today, and thank you for the rest of